A little bit about notation. We've been, for the most part, using function notation to indicate derivatives. The first derivative limit as h goes to 0, f of x plus h minus f of x over h. And then if you take the derivative of the derivative, you get the second derivative. Take the derivative of the derivative again, you get the third derivative. So in function notation, we have f prime of x for the first derivative, f double prime of x for the second derivative, f triple prime of x for the third derivative. There's another notation that is sometimes useful, and that's dy dx, and that's defined as the limit as delta x goes to 0 of delta y over delta x. So delta y would be the change in y, delta x is the change in x. So they're basically saying the same thing. Change in y. It's like the rise over the run, right? Change in x. So this is, these. If you think of these, f as y, y is equal to f of x. This is the change in y over the change in x. It's sort of the same thing, but it's a different way of expressing it. And in Leibniz notation, the second derivative is d squared y dx squared, and the third derivative would be d cubed y dx cubed. And so sometimes it's convenient to use a Leibniz notation, and sometimes it's actually convenient to combine the two different notations. We could, instead of writing f prime of x, we could write d dx of f of x, and that means the same thing. And so there's some shortcut rules, and that will sometimes be helpful to express using a Leibniz notation. One is the power rule. Derivative. So so far we've been using the definition of derivative, which can be kind of time-consuming. So these are some shortcuts that will be helpful, at least if we are taking the derivative of a function in certain forms. So the derivative of x to the n power. The shortcut rule for that is n times x to the n minus 1. Derivative of a constant is 0. Derivative of a constant times u is the constant times the derivative of u. Derivative of a sum or a difference is the sum or difference of the derivatives. And we also have the product rule and the quotient rule. The product rule and the quotient rule are maybe not quite what one would expect. The derivative of the product, you might hope that was the product of the derivatives, but that turns out not to be the case. Derivative product u times v is u times the derivative of v plus v times the derivative of u. And the quotient rule is kind of related to it. Derivative of u divided by v is v times the derivative of u minus u times the derivative of v, and the whole thing divided by v squared. So we'll I'll prove some of these rules, but before that, I think I'll go over some examples of applying them, because I think that will will help your intuition to sort of understand these rules before we start taking before we start doing the proofs. So we want the derivative of x to the 17 power, so we can use the power rule. The old exponent comes out in front, and you take one away from the old exponent. So it's going to be 17 times x to the 16. Derivative of the square root of x. Well, we don't have a separate rule here for square roots, but we can write the square root as an exponent, right? So this is equal to x to the 1/2 power, and so the derivative of x to the 1/2 power is 1/2 times x to the negative 1/2. 1 minus a half is a negative 1/2. So it's the power rule again. It's the old exponent, which is a half, and then half minus 1 would be to the negative 1/2. So we could leave it like that, or negative exponent is used to represent a fraction, so this is 1 over x to the half power, and the fractional exponents are used to represent roots, so it's 1/2 times 1 over square root of x, or we could write it as 1 over 2 square root of x. I think I did go over an example involving square roots where we were actually using the definition of derivative to get that result, but you can also use the power rule to get the same result, and usually do it quicker. On this one, we could use the quotient rule, or we could use the power rule. It's probably going to be faster to use the power rule. So we can write this as x to the minus 1 power, and so the derivative with respect to x of x to the minus 1 power, we can use the power rule. The old exponent comes out in front, and then you take 1 away, so it's going to be minus 1 x to the minus 2 power. Or we could write this as minus 1 over x squared. Okay, so that's the derivative there. Okay, so let's do like a partial proof of the power rule. I'm not going to prove it in its all its generality, but suppose we have, let's prove it for integers. For an integer greater than 2, and but it's actually true for any real number, but we'll prove it for integers. So if you have an f of x equal x to the n power, and we expand that, x of, we want to expand x plus h to the n power. S plus h to the n power, x plus h times x plus h times x plus h, etc. And if we multiply this out, we're going to get multiply all the first terms together, x times x times x times x, we'll get x to the n. And then if we multiply the, let's say x from the first term and h is from, actually we want h from the first term and then x is from the other terms, we're going to get h to the first power and x to the n minus 1. But we could have, instead of using the h from the first term, we could have used h from the second term, or we could have used the n and x's everywhere else, or we could have used the h from the last term and x's everywhere else. So there's actually n terms that will have the same result. So we'll have x to the n plus n times x to the n minus 1 times h, and then the other terms will all have a higher exponents of h, higher powers of h in them. So it would be h squared times some other terms. So if we use the definition of derivative, f prime of x is the limit as h goes to 0, f of x plus h minus f of x over h. And that's going to be, since our function is f of x equal x to the n, it's going to be x plus h to the n minus x to the n over h. And as we demonstrated before, when we expand this, we're going to get x to the n plus n x to the n minus 1 h minus h squared times some other terms. And then I've just copied the minus x to the n here. So the minus x to the n and x to the n will cancel, and we can distribute the denominator, and then we'll cancel the h's here. So we're going to be left with the limit as h goes to 0, n x to the n minus 1 minus h times some other terms. So now if we take the limit, if h is 0, this is 0 times some other term that's going to disappear, and we're just left with n times x to the n minus 1. So anyway, this proof is good for integer exponents greater than 2, but so I'm not going to try to prove it in its most general form, but it's actually true for all real numbers. Okay, so another example here, a derivative of 23. 23 is a constant, so we can use the constant rule. Derivative of a constant is 0. Okay, So that should equal 0. And here's a proof of that. So if f of x is equal to c for some constant, then and take the limit f of x plus h minus f of x over h. Well, f of x plus h and f of x are both the same constant c, right? So it's c minus c, which is 0 over h. 0 divided by h is 0. So take the limit, you can get 0 there. So I'm not going to prove all the rules, but the rules for 3 and 4 are fairly straightforward. And I'll go over later. I'll go over the product rule and the quotient rule. The product rule and the quotient rule are a bit more involved. Okay, so let's do an example here. So here we have we can combine several different rules here. So the derivative of a constant times a function is the constant times the derivative, and the derivative of sum or difference is the sum or difference of the derivative. So we can write this as f prime of x is going to be 5 times the derivative of the x of x squared minus 7 times derivative of x dx plus derivative of 4. So so that we're applying the difference, applying rules 3 and 4. We're factoring out the constants, and we're splitting up the sums and differences. So so then we can use the power rule. That's derivative of x squared is 2 times x to the first power. So this is going to be 5 times 2x. Derivative of x with this derivative of we can use the exponent rule here also. Derivative of x with respect to x. This is x to the first power. It's going to be minus 7 times 1 times x to the 0 power. And then derivative of a constant is 0. So that's 0. Well, x to the 0 power is 1. So this is just 5 times 2 is 10. So it's 10x minus 7. So the derivative there is 10x minus 7. Okay, so this this one we can do a couple of different ways. This is actually a product, so we can use the product rule, or we could expand this, multiply these out, and then use the first 4 rules. But if we use the product rule, so the product rule says the derivative of the product is that it's the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. So this is so we have the product, the quantity 2x minus 3 times the quantity 5x plus 4. So it's going to be the 2x minus 3 times the derivative of 5x plus 4 plus 5x plus 4 times the derivative of 2x minus 3. Derivative of 5x plus 4 is just 5. The derivative, and the derivative of 2x minus 3 is just 2. So it's this quantity 2x minus 3 times 5 plus the 5x plus 4 times the quantity 2. Now you can think of this, remember the derivative is basically the slope. So this is a linear term here, and it's just the slope. Y equal mx plus b, m is the slope. So it's so you can think of it that way. This is derivative 5x plus 4 is 5. Derivative 2x minus 3 is 2. And then distribute the 5 and distribute the 2. So it's 5 times 2x is 10x, 5 times 3 is 15, 2 times 5 is 10x, 2 times 4 is 8. Combined like terms, 10x plus 10x is 20x, minus 15 plus 8 is negative 7. So that's using the product rule. We could also So if we use the FOIL method to multiply this out, 2x times 5x is 10x squared. Outer product is 8x. Inner product is minus 15x. Combine those, you get negative 7x. Last times last. Negative 3 times 4 is negative 12. And then take the derivative of each term separately. So this is going to be 10 times the derivative of x squared minus 7 times the derivative of x minus the derivative of 12. So it's derivative of x squared is 2x to the first. Derivative of x to the first is 1x to the 0. Derivative of a constant is 0. So if you multiply 10 times 2 is 20, that's 20x. X to the 0 is 1, so this is 20x minus 7. Same answer we had before. So sometimes you have a choice. You can use more than one method. Here's a proof of the power rule. Proof of the power rule is more convenient in Leibniz notation. The derivative dy dx, the limit as delta x goes to 0, delta y over delta x. Delta y is the change in y, delta x is the change in x. And so we want to prove that in using Leibniz notation, the derivative of the product derivative uv with respect to x is equal to u times the derivative of v with respect to x plus v times the derivative of u with respect to x. From the diagram, delta uv, that's this box here, the change in uv is going to be u times the change in v. So this this box here, it's in the u so the original function is u times v. This is the original box here, and this box here is the next box above it is u times delta v, and this one here is delta u times delta v, and this one here is v times delta u. Okay, so the change is in gray. So uv is the original, that's in white. So the change is in gray here. These are the sort of the additional factors. So the change in the product uv would be these three boxes here. So then if we divide by delta x, so divide each term by delta x, we get delta u, change in uv divided by delta x, by the change of x is u times delta v over delta x, plus v times delta u over delta x, plus delta u times delta v over delta x. And then if we take the limit as delta x goes to 0, we get the derivative of uv with respect to x is u times dv dx. This limit of delta v over delta x as x goes to 0, dv dx. This is next term is v times the derivative of u with respect to x, and as delta x goes to 0, delta u is also going to go to 0. So it's you'll have 0 times dv dx, and then so this term drops out, and you're left with u times dv dx plus v times du dx. The proof of rule 6, the quotient rule, is similar to the proof of the product rule. So that's, but I think it's in the textbook, but I'm not going to go over it here. But I will go over an example of using the quotient rule. So this example here, we have f of x is equal to 2x minus 3 over 5x plus 4. So this is u, and this is v. Okay, so so the derivative of f prime of x, I like to write the v squared first. So it's going to be v times du dx minus u times dv dx. And this is going to be, v is 5x plus 4 times the derivative of respect to x of 2x minus 3 minus 2x minus 3 times the derivative with respect to x of 5x plus 4. And the whole thing is over 5x plus 4 quantity squared. Okay, so this is a linear factor here. The derivative is just the number in front of x. It's a slope. So it's going to be 5x plus 4 times 2 minus 2x minus 3. And again, this is a linear factor here. Derivative is just the number in front of x. That's the slope. 5 over 5x plus 4 quantity squared. And then we can distribute the 2 and distribute the 5. Next we can distribute the minus sign too. May as well distribute the minus sign. 2 times 5x is 10x. 2 times 4 is 8. Negative 5 times 2x is negative 10x. Negative 5 times negative 3 is plus 15. Over 5x plus 4 quantity squared. And then the 10x minus 10x will cancel. And we're just left with 23 over 5x plus 4 quantity squared. And that concludes this presentation.